In this video, we're going to use what we learned previously to identify asymmetric centers. An asymmetric center or a chirality center is an atom, and in the case of organic chemistry, that's usually going to be a carbon, attached to 4 different groups. These could be different atoms, or they can be different groups of atoms, and we'll walk through lots of examples on the next few slides. You might also hear the term stereocenter or stereogenic center, which is a point in a molecule that contains 2 groups that form a stereoisomer when interchanged. An asymmetric center and a stereocenter are technically different, but these terms are often used interchangeably. I'm going to draw a couple of examples right here. So if we look at this molecule I drew on the top right here, you can see that this carbon is an asymmetric center because there are 4 different groups attached: chlorine, fluorine, hydrogen, bromine. It is also a stereocenter because if I switch 2 of these groups, like the chlorine and the fluorine here, then I am going to get a stereoisomer. Let's look at one more example. In this example down here, I don't have any asymmetric centers or chirality centers. This carbon here is attached to a chlorine, a hydrogen, and a carbon, so it's only attached to 3 groups. So it's not an asymmetric center. However, it is a stereocenter, because if I exchange the chlorine and the hydrogen, I would get cis. So this carbon we considered a stereocenter, but not an asymmetric center, whereas this carbon up in the example up here is both an asymmetric center and a stereocenter. Let's take a look at thalidomide. The structure of thalidomide is shown here. This version of thalidomide was given to pregnant mothers to help with morning sickness. This version is a sedative. Unfortunately, its enantiomer was also present in the drug, and you can see the enantiomer down here. The enantiomer was a teratogen and was causing these awful mutations in the babies born to these poor mothers. Let's go ahead and identify the asymmetric carbons. It's helpful in these pictures to add in your hydrogens. So if we look right here, there's a hydrogen there that's not drawn in. So that is going to be the wedged hydrogen. There's a hydrogen down here that's not drawn in. So now we can see here that this carbon is an asymmetric carbon because it's attached to 1, 2, 3, 4 different groups. A hydrogen, a nitrogen, a carbon, and then this other carbon over here. These carbons are different, however, because this one's connected to an oxygen and a nitrogen, and this one's connected to 2 hydrogens and another carbon. So this is an asymmetric center. Down here, we also have an asymmetric center. Again, you can see that the carbon is attached to 1, 2, 3, 4 different groups. This can also be defined as a stereocenter because if we swap the hydrogen with the nitrogen, we would get the other version. If you look at the rest of the molecule, it doesn't have any other stereocenters. This carbon over here is connected to 2 hydrogens, so it's only connected to 3 different groups. Same thing with this carbon here. It's connected to a carbon, oxygen, nitrogen, only 3 different groups. In thalidomide, there were hashed and wedged lines drawn in to kind of help clue you in that there was an asymmetric center there. However, this isn't always the case. If you were given this structure here, it doesn't have any hashed or wedged lines, and you have to recognize that on the left this is an asymmetric carbon, and on the right is an asymmetric carbon. Let's draw on those hydrogens to help us out. On this left carbon here, we have a hydrogen and a methyl group attached. Those are different groups. We also have CH2s. This is where things get tricky, because these CH2 groups are actually different. Notice that this CH2 is connected to a CH, and this CH2 is connected to another CH2. That makes those groups different. So we have 1, 2, 3, 4 different groups, and so that gives us an asymmetric carbon. On the right side, we have a hydrogen, a bromine, and 2 CH2s. Again, we have to see what's attached to those CH2s. This CH2 is attached to a CH. This CH2 is attached to another CH2. Those are different groups, so we have 4 different groups attached to this carbon, and we have an asymmetric center. So if you were given this structure, it doesn't tell you anything about the stereochemistry of the molecule. It actually indicates that there are several possibilities. I could have drawn both the methyl group and the bromine up. I could have drawn them both down. Or I could have had the bromine up and the methyl group down, or the methyl group up and the bromine down. So this molecule up here doesn't have any hashed or wedged lines, meaning that it could represent any of these down here on the bottom. Let's look at a few more examples. All of these here are biomolecules that we've seen in previous chapters. For example, we have the amino acid shown over here on the left. If we look at that chiral center there, it has a hydrogen that's not drawn in. So now you can see that we have a hydrogen, a carbon, a nitrogen, and then some sort of variable R group. As long as the R group is not a hydrogen, a carboxylic acid, or an NH2, this will be a chiral center or an asymmetric carbon. Now let's look at glucose, which is a carbohydrate. I'm going to again draw in all those hydrogens there. Let's work from left to right here. This first carbon here has an oxygen, a hydrogen, a CH2, and a CH attached. Those are all different groups, so we have an asymmetric carbon. Let's look at the next carbon. We have an OH, an H, a CH, and a CH. Let's check these out to see if they're different. This CH is attached to a CH2. This CH is attached to another CH. So that means this carbon is asymmetric. Let's look at the next one. We have a hydrogen, an oxygen, a CH, and a CH. The CHs are different because this CH is attached to an aldehyde, and this CH is attached to another CH. Let's look at our last center now. We have an oxygen, hydrogen, CH, and CH attached, but this CH is double bonded to an O, this CH is bonded to an alcohol, so we also have an asymmetric carbon. Now let's look at the nucleotide in DNA. Again, the hydrogens aren't drawn in, so let's draw those in. Right here at this carbon, we have a hydrogen, a CH2, an O, and a CH attached, so that is asymmetric. Now let's look at the next one. That carbon has an oxygen, a hydrogen, a CH, and a CH2 attached, so it is also asymmetric. Over here on the right, we have a chiral center because we have a hydrogen, an oxygen, a CH2, and a nitrogenous base attached. Our last one over here is testosterone, which is a steroid, and this one has a lot of asymmetric centers. Let's go ahead and draw on these hydrogens. This first one here, we have a hydrogen, an oxygen, a CH2, and a carbon attached. So that makes this an asymmetric carbon. Next one, we have a CH3, a CH, a CH2, and a CH. These two CH groups are different. This one has an OH, and this one does not. So we have another asymmetric carbon. How about this one? We have a hydrogen, a carbon, a CH2, and a CH. So this one is also asymmetric. Now let's take a look at our next one. Hydrogen, CH, CH, CH2. This CH is different from the CH because this one is between two 6-membered rings, and this one's between a 6-membered ring and a 5-membered ring. So that is asymmetric. Next up, we have this one. It's attached to a hydrogen, a CH, a CH2, and a carbon. So it is asymmetric. Our last one here is attached to a CH3, a carbon, a CH, and a CH2. So it is asymmetric, or we can also call it a chiral center. All of the examples that we've looked at so far have been carbons. Now let's talk about nitrogen. Nitrogens are usually not considered to be asymmetric. That's because an amine has a lone pair. Interestingly, we can see that in the amine, the lone pair can actually flip sides. Nitrogen does this weird thing where it goes from being sp3 hybridized to being sp2 hybridized to being sp3 hybridized again. So that lone pair can flip back and forth. So in general, an amine is not considered to be an asymmetric center. There are a few rare cases where that lone pair can't flip, and in that case you might have an asymmetric amine, but generally this is not the case. However, if you do have an ammonium, which has 4 different groups attached and cannot interconvert, then you would have an asymmetric atom. So in these bottom cases, you can see that the nitrogen here and the nitrogen here is considered to be asymmetric. So this molecule on the left is an enantiomer of the molecule on the right, and they cannot interconvert because you don't have that lone pair there to help them flip back and forth. Make sure to work through lots of practice problems so you get really good at identifying asymmetric carbons. In the next video, we're going to look at meso compounds.